I'm going to talk today about a set of challenges. I think in particular, talking about data plane processing. This is the more application-directed processing, which is the heavy lifting within most system on chip. It can be signal processing, it can be media processing, it can be network processing, it can be security processing. The specifics are enormously varied, but the common elements are huge throughput requirements, huge throughput efficiency requirements. The degree and the type of parallelism vary widely from application to application, problem domain to problem domain. And the degree of programmability that's required in the specifics also varies pretty widely. But it certainly is growing in networking applications where the algorithms are fundamentally more dynamic. And finally, when we talk about efficiency, it's important not just to talk about computational efficiency, but also about on-chip communication efficiency. How does data get from subsystem to subsystem, core to core, block to block, memory to memory? I'm going to take some examples today from various aspects of data plane processing, focusing on networking and taking something from packet processing, from protocol stack processing, and then finish up talking about interconnect efficiencies. Because I think that there are a lot of misconceptions that I can help to illuminate. But the world in which we live is a world in which there is control plane and data plane. And the data plane is a vast mix. It's video, it's imaging, it's audio, it's protocol processing, it's security, it's all kinds of different baseband operations of different kinds. And there is a central irony associated with processors in the data plane. On the one hand, applications are evolving very rapidly. Every few years there are fundamentally new data types, fundamentally new patterns of algorithms. On the other hand, it takes a decade or more to establish a processor family, to establish an architecture, its tools, community of users. And so how can you possibly satisfy the requirements when it takes 10 years to mature a solution? And the answer is really that there is a natural partition. Some problems really are adequately solved by an application-agnostic processor, where efficiency is not so important. And that is typically found in the control plane, where all these applications look more alike. But when you are touching every pixel, every packet, every bit, and where you are expecting to do tens or hundreds of billions of operations per second in a programmable fashion, you cannot say, well, let's just throw more general purpose cores at the problem. And this is where application-specific processors have emerged, and where I think the technologies behind it are important to understand. One of the key differentiating elements among different types of data plane processing is not only the degree, but the type of parallelism which is available. And a lot of what we're doing now is trying to find better ways to exploit the available parallelism. Here is a not quite scientific, but experienced characterization of different kinds of parallelism, crudely breaking parallelism into three categories. Cases where you have data level parallelism, the same operation being done on lots of different data elements in parallel, so Cindy and vector style parallelism. Heterogeneous thread parallelism, where you have a large number of very similar threads and you want to do more or less the same category of operation in each processor on each thread. And heterogeneous threads, where you may have high-level parallelism, but it's parallelism between different styles of tasks. So baseband PHY processing, DSP processing, very heavy in vector, not as much homogeneous thread processing, though a good bit in base stations, and typically a lot of heterogeneous thread processing. Imaging, lots of thread parallelism and lots of vector parallelism. Audio, quite a bit of data level parallelism, much less thread parallelism typically available in these applications. Networking, very, very little data parallelism. You really have a lot of sequential processing, sequential interpretation of protocols, applied, for example, to packet headers. But lots and lots of packets in the aggregate stream, and therefore lots of opportunity for homogeneous threads. And the generic application, running Excel or running Angry Birds, not a lot of parallelism really to be had in any of these three flavors. So what does this mean? It means that we are dealing with opportunities to accelerate the performance of these processors in order to accelerate the performance of the application. One element of that is configurability. That is, to be able to pick and choose the DSP subsystems, the memory subsystems, the specific packages of execution units, and all of the characteristics, including instruction fetch and issue width, data mode store width, to be able to scale over 2 orders of magnitude in terms of computational throughput, and to get real-time feedback on that. And that's all within this notion of point-and-click configurability. We often want to think in terms of also extending the interfaces of the processor, because certainly there are few applications which can do an infinite amount of compute on a 32-bit data stream. If you're going to scale computational performance, you're also going to need to scale the throughput from memory and from other kinds of data streams that are running through your system-on-chip architecture. And so one of the things we've done is define an entire language, the Tensilica instruction extension language, which allows for complete reconfigurability and extension of the instruction set and the interface of the processor, including 3 distinct types of new interfaces. Ports, which are wires in and out of arbitrary width that become operands in the operations of the processor. Queues, which include the complete data streaming handshake in order to do hardware flow control so that you can stream thousands of bits per cycle without any handshake stalls in and out of the processor. And lookups, which essentially create additional address spaces of arbitrary width so that it's quite reasonable to say, oh, I need a processor which does 22 memory references per cycle. Perfectly reasonable thing to do if your application has that specific kind of parallelism requirement. Let me dive for a moment into the characteristics of the Thai language, because I think it's important to understand the flexibility that's implied. It is a language which allows you to describe at a high level the semantics, the operands, and the pipeline schedule characteristics of a pretty arbitrary computational problem. Any number of operands, the operands can be of arbitrary width, thousands of bits wide is fine, and can describe the bundling of these operations into VLIW packets so that you can have a dozen or more of these thousands of bits wide operations being issued in parallel per core. That gives you this enormous headroom for computation. Yet it's quite a simple language. There's an example of a population count. It essentially allows you to express anything that could be expressed logically in Verilog as a computational operation, now wrapped inside of the operands and the compiler support that makes that fully visible to the average C programmer, including things like automatic vectorization of code. And this capability is widely used. Within the Xtensa architecture, which is now licensed by about 200 companies, we announced today the delivery of the 2 billion Tensilica core. There are more than 5,000 variations of the Xtensa architecture, which have been taken as production designs by our customers. So this configurability and extensibility is very real, and it is the key to getting the computational throughput to a level of efficiency, an order of magnitude beyond what you get from generic application agnostic processor cores which dominate the control plane. So now let's dig a little bit deeper into a few applications, starting from this somewhat abstracted view of network packet forwarding. you have a very intense stream of IP packets. And here we see the relatively complex structure of packets coming into typically some kind of a packet distributor, which could be either processor-based or hardware-based, to a set of packet processors, often a very large number, though I'm only showing 4 here, which have a set of resources, often for CAMs, TCAMs, other kinds of memories that need to be kept busy. In fact, the real cost of these kinds of systems is often in the TCAM and memory interfaces, and the job of the processor subsystem is to saturate the available bandwidth. So you want to, with as easy a programming model as possible, have as many requests going into that scarce resource. And then finally, you have analyzed packets coming out the other side. Their headers have been transformed, statistics have been gathered, they are being routed to quite a range of different outgoing queues, and they are reunited with their payloads. One of the ways this may work, and this is an example of using this very wide data interface, in this case the very wide load-store interfaces. You have general purpose tightly coupled memories, the local data RAMs of the processor, but where you can simply configure those memories to be 512-bit wide per cycle, coming into some internal register file and register state, and have a set of operations which in one or more likely several cycles will analyze and transform that packet header and prepare it for output. And so with just a few cycles per 512-bit packet header, you're fully able to analyze forward that header. And because you're building on top of a very lean processor at its foundation, just over 10,000 gates for a 5-stage pipeline, 1.2 gigahertz core, as the lowest level building block, you are able to run at very high speed with very small hardware cost associated with the replication of these cores. In cases like this, where there is significant available thread parallelism. This is on accelerating processors for wireless stack processing. So this is not the normally considered massively parallel SIMD-style baseband processing, but up in layer 2 and layer 3, where you are doing things like doing the MAC HS protocol. Now, this is a very densely packed header structure. You can see that everything is on bit alignment. And so a conventional processor typically spends a lot of cycles to extract all of these different fields and then perform the various transformations using those field values. What Professor Fettweiss and his colleagues have done is configured a tensilica processor, an Xtensa processor, with a simple set of bit-level processing extensions that allow it to stream these arbitrary variable length headers through the processor, extracting and setting various bits within the header, and seeing typical improvement in the efficiency of the cores as measured by 1 over the area time power metric compared to other very good processors, x86 Atom, Cortex R4, a really substantial speed up, a very substantial efficiency advantage for a relatively small number of extensions, a cost of a little over a 1/100th of a square millimeter of hardware added to the processor to get this on the order of 10x improved. Now let's think a bit about interconnect, because all the processing acceleration in the world isn't really going to help system-on-chip throughput unless you're also correspondingly improving the efficiency of interconnect. And there are a number of different dimensions of the interconnect problem to think about. How are you going to handle the total bandwidth? What is the pattern of access? Is it core-to-core mostly, or is it core to off-chip DRAM? How big is the working set? And if you look at networking versus baseband versus imaging, you have orders of magnitude increase in the working set size from one of those application classes to the next. And you're going to build very different memory systems, typically, if you're going to be optimal for those different cases. Plus, the access patterns are very different. Imaging has a great sequential locality. Networking, sometimes not so much. And there's a lot of variability in the sizes and patterns depending on how dynamic the algorithms are. So there are a few rules of thumb or principles that come out from building these multi-core configured processor subsystems. One of them is, remember that the energy associated with moving data around is proportional to distance. Going across the chip costs 10x or more than talking to the core immediately next door, and going off chip costs more yet. In fact, I have a little bit of a personal rule of thumb. If you can talk just with a wire that goes from core A to core B, that may cost you 1 unit of energy. If you have to read and write a memory to communicate, I write it, you read it, that's probably 4x that amount of power. If you have to go across an on-chip network, that's another 4x more power. And if you have to go off-chip to DRAM to get it, it's not 4x more energy than that, it's probably 16x more energy than that. So you have almost 3 orders of magnitude difference in the energy cost for communication between the most simple core-to-core wire communication, which is partly why RTL sometimes looks good, because they often go and settle for something with just a wire kind of communication channel. And at the other extreme, if everybody's saying, well, I don't know how big it is, or where it is, or when it is, so I'll just shove everything into DRAM, very expensive for an energy saving. So that allows us to think about a more diverse vocabulary of topologies that we might use to connect up a set of cores. The classical model for multi-core is often multiple cores, homogeneous, symmetric, cache coherent, multiple levels of cache. So you have L1 caches, you have coherency hardware at each level, you have L2, you often have L3, you have DDR, and there's lots of traffic both up and down the hierarchy and between cores with a fairly significant handshake that takes place every time a core needs to look beyond its own cache. In embedded systems, you often do know something about the data pattern, and you're willing to adapt the programming model, for example, to move data more explicitly. So DMA channels in the center top have a significant opportunity to hide latency even better than the cache hierarchy, and to do it with less energy because you don't have as elaborate protocol. You can sometimes dispense with DDR entirely if your working set size is smaller, and you get to the picture in the upper right. One of the models which has turned out to be very valuable, rather than centralizing memories, is to keep all of the memory visible to all of the cores, but to distribute it physically. So it is a distributed shared memory, where a processor will tend to work on the data which is local to itself, and will only go to the uniform shared memory portion which happens to live next to a different processor when it is needed for those relatively rare core-to-core transfers. You can take this another step further and say, well, rather than go out on the bus, if I know that I'm either talking to my local memory or I'm talking to the memory of just one other core, I can physically associate these cores so that I can build a rather short, low power, low latency link from core to core. And you start to introduce a degree of application specificity in the topology of the network. So if you have some foreknowledge of what the pattern is likely to be, and the harder you study an application, the more you know about the likely patterns, then you can optimize for that. And finally, in the lower right, you can see an adaptation of this that not only has local links, but has a global chain, a low-cost connection that allows you to go from core to core uniformly, yet spend most of the traffic. Most of the energy goes just into these low energy links. We can do a little comparison here. And in a nutshell, we're comparing 3 different energy models using real layouts, real synthesis, and applied to a bus-based cluster with cache coherency, a bus-based cluster with DMA transfer among cores, and a local link transfer. Core A is writing to memory of core B. And we built up this model with 128-bit links, and then we applied a really high bandwidth problem. In this case, the computational bandwidths taken from an LTE Advanced PHY baseband, which totals about 6.5 gigabytes per second across multiple cores. And so what we find is not modest differences. This is the power per million 128-bit transfers, where the cost of a direct link, I write your memory, is down around, I think that's about 20 microwatts per mega transfer. If you apply the same technology, but scale appropriately to the increased logic, the increased distances that you have to travel, and the number of transactions that have to take place on memory as you snoop caches, for example, you get about 30x more energy associated. So it adds up to pretty big numbers. So to wrap up, the key of data plane processing is to find the right architecture to exploit the parallelism you actually have in that application. And where that parallelism is not just a computational parallelism, it's parallelism across compute and communication. Extensibility is a very potent tool. It's very widely used today, and it really leverages the fact that you need often orders of magnitude increase in bandwidths as well as compute. Parallelism has lots of data networking has lots of parallelism to exploit, and there is a huge range of problems that can be solved in this variety of ways. So, and the final thing, let's be scientific about it. Intuition sometimes doesn't work very well on these systems, so modeling is critical. So model, 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 measure, 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 don't guess. Thank you very much.